You have seen AI build flashy demo apps and generate pretty pictures. This is different. This is the daily, non-sexy DevOps work I do with GLM 5.3. And today I finished the day on the official GLM 5.3 Flash, Ox Alpha, in Z-code. 3 sessions, 1 real platform bug, a running pod patched live. Dispatch. Here is the puzzle: a big enterprise platform, web shop, enterprise API gateway, and a proxy layer that fans out to microservices, started failing every checkout call with a cryptic error, code -5, possible routing failure. But the microservice behind the proxy answered 200 OK on every single request. Business logic was winning, only the envelope was broken. For days, nobody could even see where to look. This story is really 3 sessions of pairing between an engineer and GLM 5.3 Flash. Session 1 built the weapon, a load test suite that drives the whole buyer phone journey, staged so it can never place a real order. Session 2 hit the wall. Every qualification call returned -5 and traced the failure through 3 layers of platform. Session 3 is today. Reproduce it locally, kill the wrong theories, and patch the bug while the service keeps running. The decisive clue was 2 logs disagreeing. The ingress component rejected the response. It saw content length and transfer encoding on the same message, which the HTTP specification forbids, so it answered 502. 1 layer back, the business service had answered 200 OK to 100% of those calls. The message body was never corrupted. The envelope was. Here is the crime scene, simplified but real. A load test client hits the enterprise API gateway, which forwards through an ingress to a Spring Boot proxy layer, which fans out to microservices. The microservice answers a perfectly legal chunked 200. The proxy copies that response's headers verbatim, including the hop-by-hop transfer encoding, then stamps its own content length on top. 2 framing headers on 1 message. The ingress is required by the spec to treat that as an attack attempt and reject it, and the gateway wraps the whole thing as -5. The test domain is a full customer journey. Discover a device and plan, qualify eligibility, build and validate a cart, complete checkout, and only then, behind a safety gate, place an order. 5 phases, 5 different microservices, identifiers chained forward. What made this defect vicious? The -5 mask hit 3 of those phases at once, so the whole journey looked broken from the client, while every server-side dashboard stayed green. Reading the proxy's decompiled source, the whole defect is 4 lines. A filter copies every upstream response header onto its own response, and transfer encoding is hop by hop. It describes 1 connection only and must never be forwarded. Then the same class force sets its own content length over a raw body. The specification says a sender must not produce that combination. The proxy has been producing it on every chunked upstream since the day it shipped. The vendor's fix is a 2-line hop-by-hop guard, and until it lands, this pod ships the bug. Before touching the cluster, every theory had to survive an experiment. Rolling back the proxy build fails identically in a local Docker rig. The popular theory that ingress buffering reframes responses, disproven on the wire. Chunked stays chunked, making the ingress lenient. Impossible. The rejection is a hard-coded parser check designed to stop request smuggling. What survived? A minimal lab that reproduces the 5002 with the real image and flips it to 200 with a patched jar. Evidence first, opinion second. The way up was disciplined. First, a local Docker rig with the real proxy image and simulated upstreams. The defect reproduced in minutes. Second, everything became a script. Idempotent commands that converge to the same state. Fail-fast checks that stop the moment reality disagrees. Third, the lab proved the flip. Attach a patching agent to a running, broken Java process, and the same request goes 5002 to 200 with no restart. Only then did the same script, in its cluster flavor, get pointed at the real pre-production pods. Here is the trick that is not a trick. The Java virtual machine has a built-in attach interface. It is how every debugger connects. A tiny tool asks the running process to load a small instrumentation agent. The agent retransforms one already loaded class at the single choke point every servlet response passes through and weaves in one rule. If the header name is transfer-encoding, drop it. No restart, no new image, no Kubernetes objects touched. The proxy simply loses the ability to say the thing the specification forbids. This is the entire patch. 2 rules, 4 lines each, against one class. Tomcat's response facade, the component every servlet header write must pass through. At method entry, if the name is transfer-encoding, return without setting it. That is the vendor's recommended fix, a hop-by-hop guard applied at runtime instead of in the jar. Tomcat frames the body itself afterward, legally, the way it always does when the application stays out of the way. The discipline is what makes this engineering instead of hacking. The script is idempotent. Run it twice, you get the same state, because reattaching just reinstalls identical rules. It is fail fast. A stale target or wrong user fails the pre-flight instead of patching something unexpected. The blast radius is one pod. The agent lives in memory and temporary storage, and reverting is literally deleting the pod. And a canary test fails loudly the moment the -5 mask ever comes back, so nobody mistakes the patch for the fix. Then the moment. All 3 replicas patched, one command. The same checkout call that returned -5 for days returned a real 200, with the full business verdict inside. Checkout validation, which had been an opaque wall, returned its actual validation ladder, and by the end of the session, the test suite drove the entire checkout flow to a genuine 204 no content. 102 checks, 30 seconds, 0 -5s anywhere. The mask didn't get fixed, it got removed. Now the honest question. Isn't this reckless? The evidence says otherwise. The attach interface is a designed door. Debuggers walk through it daily, and the pod's own security policy explicitly allowed same user access. The blast radius is one pod, memory only, reversible by deleting it, with a canary that screams if the patch silently matters again. And it was disclosed. A root cause ticket with the full analysis went to the platform vendor, whose code fix remains the actual fix. A hack stays legitimate only while everyone knows it is there. The engineer's own words at the end of session 3, amazing and scary that this works. The amazing part is a defect that hid for days behind 3 layers of platform, killed in an evening by a 2-rule patch and a 100-check suite. The scary part is the general lesson. In any Java estate, 1 rule file can change runtime behavior with no governance hook watching. That asymmetry is worth knowing about, whether you are the one holding the tool or the one who should be watching for it. If you want more AI pairing sessions that end with a running platform actually fixed, subscribe. We follow the receipts, we reproduce before we believe, and we show you the whole ladder. See you in the next briefing.